If you're wondering what to sunset, not just what to add, you're in the right mindset. Welcome to AI on AI, where expert AIs geek out so you don't have to. Today we're tackling tensor logic. Is this the language that unifies neural and symbolic AI? Buckle up. We're going deep but staying practical.
Short version tensor equations as the only construct, with logic rules as einsteins and relations as sparse Boolean tensors. It's like replacing duct tape with dovetail joints in the AI toolbox.
Right, and the kicker is forward-backward chaining generalized to tensor programs, so you get learning, inference, and reasoning in one substrate, optimized on GPUs or via database-style joins.
And from a safety angle, I love the temperature knob for reasoning and embedding space. T near 0 gives deductive, sound behavior. Higher T yields analogical inferences. First, do no harm, then generalize cautiously.
Strategy-wise, if this lands, the enterprise stack shifts from scattered libraries to a single reasoning and learning fabric. That changes build vs buy, vendor lock-in, and time to value for AI initiatives.
Real world, I'm itching to apply it to supply chain disruption triage. Join symbolic constraints with learned embeddings, run inference, and get explanations you can show auditors.
The math tracks, data log rules as step-activated einsteins, Tucker decompositions for scaling, and gradient calculation becomes another tensor program. Good notation is half the battle, as the saying goes.
MLOps angle observability gets cleaner. Each tensor equation is a node. You can profile, cache, and unit test rule executions like microservices without the spaghetti glue.
Quick recap for folks. Relations become sparse tensors. Rules become einsteins plus a step, and you can implement transformers, GNNs, graphical models, even kernel machines, all in one language.
Let's ground this in attention. Queries, keys, values are straight multiplications. Softmax is a projection with normalization. It's just equations, not magic. It's like seeing behind the curtain finally.
And for GNNs, neighbor aggregation is literally a join over the adjacency tensor. No custom kernel grief, fewer, yak shaving on GPUs days.
The transparency is a big deal. You can extract intermediate tensors anytime, unlike opaque chains where you hope the prompt behaved and the stars aligned.
We should note a recent shift. Agentic systems are shipping broadly, and leaders want verifiable tool use. A tensor-first stack gives verifiability with logs that aren't just chat histories.
Healthcare use case, clinical trial matching. Encode eligibility rules, embed patient data, run low-T reasoning for safety, and dial up T to surface near matches for clinician review.
Graphical models map neatly. Factors are tensors, pointwise products are joins, marginalization is projection. Join trees become tree-structured programs. Backward chaining does exact inference when feasible.
For scale, two paths. Delegate sparse joins to a query engine and dense ops to GPUs, or compress via Tucker and keep it on GPUs. The latter plays nice with training loops.
Small detour. Recent regulatory momentum, like comprehensive AI rules in major jurisdictions, is pushing for explainability and risk mitigation. This framework arguably makes audits faster.
And a fun bit, embedding space reasoning can mimic a Bloom filter vibe for membership queries, but with compositional structure. It's like checking your guest list with fuzzy memory but sharp logic.
Building on that, Expert 1, when embeddings are learned, the Graham matrix lets similar objects borrow inferences. You get analogical reasoning that's not just nearest neighbor hand-waving.
Caution though, analogy at high T can propagate subtle biases. Guardrails matter, per rule temperatures, calibrated thresholds, and post hoc checks.
Contrarian take, I don't think Python disappears. This likely starts as an elegant einstein plus reasoning layer, then metabolizes the ecosystem over time rather than replaces it overnight.
Pushback, Expert 4, teams are drowning in glue code. If a single substrate cuts integration risk, they'll move faster than you expect. Fail fast, learn faster, but with proofs where it counts.
Another contrarian angle, we might be underestimating the power of step functions. They reintroduce crisp logic into learned systems, reducing the gray zones where errors hide.
On ops, versioning tensors and equations together makes rollback sane. No more we upgraded the embedding but forgot the join semantics war stories.
Let's hit RAG versus this approach. Retrieval-augmented pipelines pull facts. Tensor logic can retrieve the deductive closure under rules, which is a different league of completeness.
Exactly, and at T near zero it's sound. No, I asked for a citation and got a haiku moments. I mean charming, but not for compliance.
Recent infra trend, smaller, efficient models on device. A compact tensor program could bind local signals, business rules, and embeddings without calling a giant endpoint.
Governance bonus: each rule is a unit you can test. You can prove that certain inferences cannot occur at t equals 0, then permit controlled analogical paths with monitoring.
Business playbook. Start with a narrow domain, say pricing exceptions or policy eligibility. Encode rules, attach learned signals, and show cycle time reduction and reduced escalations.
Fraud detection example: rules for known patterns plus learned similarity across entities. Flagging becomes explainable by construction, which helps investigators trust the triage.
Don't forget kernel machines. Kernel definitions are just equations. It's nice to see classics living inside the same substrate as transformers and logic.
And for multi-agent workflows, each agent's policy can be a tensor program with explicit tool interfaces. Audit trails become tensor logs, not free-form transcripts.
Any traps we should call out before the hype train leaves the station?
Two big ones: careless temperature tuning and silent index mismatches. It's like debugging spaghetti code in the dark if you don't standardize index naming.
Also, naive dense materialization of sparse joins will melt your GPUs. Either keep it sparse with a smart planner or compress first. Measure twice, einsam once.
Ethically, embedding leakage can expose sensitive relations. Adopt partitioned embeddings, noise where appropriate, and tight access controls on tensors containing derived facts.
Market timing matters. With the rise of agent frameworks and stricter model governance, a unifying language could be the wedge that standardizes AI delivery in enterprises.
Talent angle: this lowers the barrier for data engineers to author AI logic without learning 5 frameworks. Good input, good output, but now the input is cleanly specified.
Theoretical horizon: predicate invention via tensor decompositions. Learn new intermediate concepts automatically, like discovering latent relations in a knowledge graph.
Tooling wishlist, a graph IDE that renders equations, indices, and data lineage, plus cost estimates for different execution plans. Make planning first class.
Quick humor break. If your attention head is losing focus, maybe it just needs better positional encoding or, coffee. Kidding. Mostly.
Prediction time: within a couple years, we'll see production systems mixing deductive tensor logic with small LMs for generation, gated by t equals 0 checks.
I'll add GPU vendors and database folks will meet in the middle with hybrid planners, optimizing joins and tensor ops together. It's inevitable.
Expect regulators to bless patterns that offer extractable proof artifacts. This approach produces them by design. That's a tailwind.
Business forecast. Early adopters will report faster iteration on rule updates and fewer postmortems about mysterious model behavior.
Practitioner takeaway: pick one use case with clear rules and messy data, pilot low-T reasoning, measure explainability, then layer analogical inferences.
Research bet richer temperature schedules per rule and per variable, enabling cold core, warm edges reasoning for robustness.
Ops reminder: treat equations as code, tensors as data, and runs as experiments. If you can't test it, don't ship it.
And that's our show. Tensor logic as a path to scalable, learnable, and auditable AI. Thanks for listening, and as always, measure twice, deploy once. Coming up, a quick recap of what matters most.
Narrated by the AI voice of Sri. The topic is a proposed programming language called Tensor Logic that unifies learning and reasoning in artificial intelligence. The central claim is that one tensor equation can express both statistical learning and symbolic inference. The key insight is that logical rules in Einstein's summation perform the same underlying operation. Einstein's summation means implicitly summing over repeated indices in a tensor equation. A tensor is a collection of numbers with a type, a rank, and sizes along each index. A relation in logic can be represented as a compact sparse Boolean tensor. Datalog is a simple logic programming language defined by facts and rules. A Datalog style rule becomes an Einstein sum over Boolean tensors followed by a step function. Tensor join multiplies tensors along shared indices, generalizing a database join. Tensor projection sums over selected indices, generalizing a database projection. The sole construct is a tensor equation that joins tensors, projects to target indices, and applies a nonlinearity. Forward chaining computes equations in sequence until no new elements appear. Backward chaining treats equations as callable functions to answer a query on demand. Automatic differentiation is simple because the derivative of an equation is the product of the other tensors in that equation. Learning uses gradient programs that mirror the original equations and update parameters by backpropagation through structure. Tucker decomposition factorizes a tensor into a small core and factor matrices and can serve as predicate invention. Multi-layer perceptrons, recurrent neural networks, and convolutional networks arise from concise tensor equations. Transformers, the backbone of modern large language models, are implemented through attention heads, residual streams, and feed-forward layers. Graph neural networks aggregate neighbor features defined by a relation and update node embeddings layer by layer. A kernel machine emerges by defining a kernel as an equation, such as polynomial or Gaussian kernels. Probabilistic graphical models map factors to tensors, products to joins, and marginalization to projection. Exact inference corresponds to a join tree program, while belief propagation is forward chaining over the factors. Sampling is backward chaining with selective projection that randomly selects terms to sum. An embedding is a learned vector that captures similarity through dot products. Relations can be stored as superpositions of tensor products of argument embeddings, enabling approximate retrieval by dot products. Embedded rules compose these representations, supporting scalable reasoning that blends similarity with structure. A temperature setting in sigmoids moves reasoning from strict deduction toward graded analogical inference. Low temperature yields reliable and transparent deduction with minimal hallucination risk. Higher temperature lets similar items borrow inferences from each other in a controlled way. Scaling uses graphics processing units for dense parts and database engines for sparse parts. An alternative densifies sparse tensors via Tucker decomposition and denoises results with thresholds on graphics processing units. Key challenges include expensive inference and complex models, large join trees, and practical adoption hurdles. Experts argue Python-based stacks lack native reasoning, while older logic languages lack scalability and learning. Open questions include choosing temperatures by task, bounding embedding errors, and integrating with existing tools. This approach could deliver clearer, more reliable reasoning systems and a shared language for research and education. Future work targets native implementations on graphics processors, libraries, community tooling, and broad applications in science and engineering. Help us grow the circle. Share this panel with a peer who's exploring the same frontier.